Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. Welcome to Physics Live Lecture, Physics EP025. I'm Panjamila binti Murad and my turn is to discuss about capacitors and dielectric, which is topic chapter 2 for EP025. Okay, for this topic, capacitors and dielectric, the topic of capacitors and dielectric, actually we have three subtopics, which are, the first one is about capacitors, and then we look into charging and discharging of capacitor, and the third subtopic is about the dielectric. Okay, for the capacitors, we are looking into the circuit of when you have the capacitor in the circuit, when you connect the capacitors either in series or in parallel. Okay, for the first subtopic, capacitor and capacitors in series and parallel. Here we have three main objectives. The first one is define and use capacitor. Equation of capacitor is C equal to Q over V. Okay, and then determine the effective capacitance of capacitors in series and parallel. And the third objective is use energy stored in capacitor, whereby you have three equations here. You can use either equation U equal to half CV squared, or energy stored equal to half QV, and also the third equation half Q squared over C. Okay, three equations we look into it after this. Okay, the term capacitor. Okay, for this diagram show you the variety of capacitors. Some in smaller size and bigger size. So what is a capacitor? The word capacitor or the term capacitor refers to the device that can store electrical energy. When you store the charge, they will have electrical energy stored in this electric field. Okay, capacitor is constructed of two parallel conducting plates separated by an insulator. This is the simplest form of the capacitor. It can be in cylindrical form or spherical. But here we look into the two parallel plates only. For our syllabus, we look into two parallel conducting plates. Okay, the symbol used when you draw the circuit diagram, okay, this is the figure to be used, or the symbol to be used for a capacitor. Normally we use this one on the left hand side. So the use of capacitor, first one is heart defibrillator. It is used by personal medicine in hospital to reset the heartbeat. And then camera flash unit, for example. So it is a part of electronic circuit used on computer. It can be micro-size on computer chip or super size. Comes in variety of shape and size. That is the capacitor. What is the capacitor? Then the term capacitor. To differentiate between capacitor and capacitor, okay, let's say you have two parallel plates, which is the capacitor. Then you connected it to the power supply. When a capacitor is connected to a battery, so the charge will move. Okay, I'm talking about the current where the positive charge is the charge carrier. So the positive charge from the positive terminal of the battery will move to the left hand side plate. So this plate will acquire negative positive charge. And then for the right hand side plate, so it will acquire negative charge. The same amount of positive and negative charge onto the plate of the capacitor. So relationship between capacitor, voltage applied, and then the charge on the plate of capacitor. Q equal to CV. Okay, capacitor actually the symbol C here is for the capacitance. Capacitance is a property of the capacitor. So capacitance is a measure of capacitor's ability to store charge on its plate. As I said just now, it is the um, property of the capacitor itself. In terms of definition of the capacitor, define and use capacitor. For the objective number one, define the capacitor. So in terms of definition of the capacitor is the ratio of the charge on either plate to the potential difference between the plate. So C equal to Q over V. Okay, for this mathematical relationship, Q stands for the magnitude of the charge on each plate. V is the potential difference across the two plates. And then the unit is Farad, Michael Faraday, based on his name. Okay, C equal to QV. When you look into this question, it doesn't mean that C proportional to Q or V. It not depends on Q or V. C is a property. Capacitance is a property of the capacitor. It doesn't depend on Q or V, but Q and V depend on the capacitor. Capacitance is the storage of the capacitor. How large is its storage? It doesn't depend on Q and V. Okay, definition of 1 farad. Okay, capacitor has a capacitance of 1 farad. The value of its capacitor is if 1 coulomb of charge is deposited on the plate by a potential difference of 1 volt across its plate. Okay, you need to have 1 farad of the capacitor. So the charge is 1 coulomb per voltage applied is 1 volt. Okay, normally our capacitor is very small in size, 10 negative 6, 10 negative 9 or 10 negative 12. When you buy a capacitor, so if you printed there, what is the capacitance of the capacitor? You can see the storage of that capacitor is equal to its capacitance, its ability to store charge. The higher its capacitance, meaning that its ability to store charge is higher also. Then we come to the second objective, which is determine the effective capacitance of capacitors in series and in parallel. So when we wire capacitor in a circuit, we need to identify whether we wire it in series or in parallel. Okay, for this figure here, okay, you can see the positive terminal of the battery. Okay, this arrangement of capacitor, we say it is in parallel. Okay, how to connect the three capacitor that you have here in parallel? So look at the terminal of the battery, positive terminal here. Okay, you should connect it to the positive terminal of the capacitor. Also to the positive terminal of capacitor number 2 and positive terminal of capacitor number 3. Capacitor is a circuit connected by wires such that the positively charged plate are connected together and the negatively charged plate are connected together, we say that the connection are in parallel. This again refer to parallel connection. How about series connection? Capacitors wired together such that the positively charged plate of one capacitor is connected to the negatively charged plate of the next capacitor are connected in series. Okay, looking at this picture, positive terminal of the battery. And then for the plate of the capacitor connected to positive plate of the capacitor on the top of it, and negative plate, C2 top of it is positive plate, C3 also top of it is positive plate. So we say this connection is series connection. How to determine whether your circuit diagram, the capacitors connected in series or in parallel, you should have a skill how to look into the connection of more than one capacitor. So this one, okay, when the capacitor or other device connected along a single path are said to be connected in series. Okay, the charge move here, okay, from the battery when the circuit is completed, okay, and then it moves to capacitor one. This one will have the plate on the left hand side require positive charge. So there will extra positive charge here. Then the positive charge on the negative terminal will be repaired. Okay, you learn about this in topic 1, repulsive force between the same sign of charge. C1, C2. Okay. For series connection, okay, this is how to connect the capacitors in series connection. Positive terminal, negative terminal, and so on. And you wire. This is the first capacitor. This is negative terminal of your first capacitor, and then you wire it to the positive terminal of the second capacitor. Positive to negative, and so on. In using equation C equal to Q over V or Q equal to CV, we will look into charge on capacitor in series. Conclusion that we can make when you have capacitors arranged in series, the charge on each capacitor is the same. Characteristic of capacitors connected in series in terms of the charge. So the charge on each capacitor is the same. Okay, Q, total Q delivered from the battery, so it will equal to Q1, Q2 on capacitor C2 equal to Q3 on capacitor C3. So the charge is the same for C1, C2 and C3. And then voltage. And for our equation, we have Q equal to CV. In terms of the charge, this now is the same about the voltage on each capacitor arranged in series. Okay, for this, okay, so we connected to a battery, 3 capacitors connected to a battery. Then what happened to the potential against capacitor 1, capacitor 2, and capacitor 3? Potential difference between point A and B is independent of path. You learn it in previous chapter, previous topic. The battery voltage must equal to the sum of the voltage across each capacitor. So this is the conclusion for the voltage. In terms of the voltage, okay, V from the battery. So it should equal to V1 plus V2 plus V3. Let's say your battery use is 12 volt. So it depends voltage across each capacitor. Okay, the charge is the same, so you use Q equal to CV. So when Q equal to CV, Q is the same, you can arrange this equation, then you get the total of V across V1 plus V2, V3 is equal to the voltage from the battery supplied by the battery. That is in terms of voltage. Q is the same for capacitors in series, so the higher capacitor will get lower voltage. Q equal to CV. Q equal to CV. Q is the same for all three capacitors. Voltage is different. The total equal to the voltage supplied by the battery. How about the equivalent or effective capacitance? The word equivalent or effective refer to the total capacitance. Let's say here you have three capacitors connected in series to a battery of voltage V. You have C1, C2, C3. Okay. Equivalent capacitor meaning that you want to total up these three capacitors, just like you have here three storage, three capacitors with each individual capacitor, and then you just want to total the three capacitors just as one capacitor, which we call as C effective. So you have this one capacitor which is C effective, then the total voltage here should equal to the voltage supplied by the battery. Okay, if you have any question, please text under chat section. Okay, the total potential difference across when you have C1, C2 arranged in series. Okay, just now as I said, the total voltage from these three capacitors equal to the voltage of the battery. So by substitute Q, each capacitor get same amount of charge accumulate on each plate of capacitor is the same. So Q for V1 is Q divided by its capacitor. For C2, okay, total charge on its plate divided by its capacitor plus V3, Q equal to CV, so V equal to Q over C. Q here is, we name this as just Q without the subscript, and then C3 refer to capacitance of capacitor number 3. Q is the same, so V over Q equal to 1 over C1. We rearrange this equation plus 1 over C2 plus 1 over C3. So you get 1 over Q equal to 1 over C effective. 1 over C1 plus 1 over C2 plus 1 over C3 is 1 over C effective. So effective or equivalent capacitance for the number of capacitors in series is given by this equation. 1 over C effective equal to 1 over C1 plus 1 over C2 plus 1 over C3, dot. How many capacitors that you have arranged in series. Okay, we move on to parallel circuit. When you arrange the capacitor, here you have three capacitors connected in parallel. So capacitors which are all connected to the same source of potential are said to be connected in parallel, referred to the circuit diagram here. Positive to positive, okay, positive terminal of capacitor 1 to positive terminal of capacitor 2, and from positive terminal of capacitor 2 connected to positive terminal of capacitor 3. So it is arranged, the three capacitors here arranged in parallel. We need to look into its effective capacitance. Okay, in terms of voltage, okay, VT refer to V total or V from this battery here, supply voltage from the battery or your power supply, equal to V1, equal to V2 and V3. The voltage from the power supply or the battery, okay, the charge move and complete the circuit, so the voltage across the battery equal to the voltage across C1. If the charge move from the positive terminal of the battery here and it move through C2 and come back to the battery, so the potential across C2 is equal to the potential across the battery. Same goes for capacitor 3 in terms of the voltage of each capacitor. Okay, in terms of charge, Q total. Q total is from the battery equal to Q1. Q1 is the total charge on plate capacitor 1. Q2 refer the total charge accumulate on capacitor 2 plus Q3. Total charge on capacitor number 3. Q equal to Q1 plus Q2 plus Q3. Okay, to determine equivalent or effective capacitor in parallel circuit, the capacitors, okay, we replace it with an equivalent capacitor. The three capacitors here, in order to just get one capacitor or one capacitor equal to C equivalent. Okay, by looking into the charge, okay, total charge is now, question of total charge, Q equal to Q1 plus Q2 plus Q3, and then you substitute, okay, Q1 charge on plate Q1 is equal to its capacitor, the value is capacitance C1 times the voltage, okay, same voltage across each capacitor plus capacitor 2 is capacitance times the voltage plus C3 times the value of capacitance of capacitor 3 times the voltage. So rearrange the equation okay, Q over V equal to C1 plus C2 plus C3. From the equation, Q over V equal to C, so total charge per total voltage equal to total capacitance, which we call as C effective. So your C effective, total Q over V. Okay, C effective is C1 plus C2 plus C3 plus dot dot dot. Okay, just now C, okay, recall back in series, 1 over C effective is 1 over C1 plus 1 over C2 plus 1 over C3. But for effective capacitance parallel connection, you just plus the capacitance of each capacitor, C1 plus C2 plus C3, so on. We still in subtopic 2.1. The third objective is use energy stored in a capacitor. Okay, when a swing closed, charges begins to accumulate on the plate of capacitor. So charge flow from the battery to the plate of capacitor. So the charge is the plate of capacitor will have a charge positive on its positive terminal and negatively charged on its negative terminal. Concept of work and energy store. Okay. To summarize, okay, work is done by a battery. Battery bring a small amount of charge from to the capacitor. From the battery to capacitor. Okay, dW equal to V dQ. I move very fast because we don't need to know all these equation. Just how to derive the equation of work, the equation of energy store. Work equal to the energy store. So work is done by the battery. Work done required to increase the accumulated charge from 0 to Q. So this is the equation to be used in order to calculate the energy stored in a capacitor. Basically, you have three equations here. The first one is half Q square over C, or you can use equation half CV square. And then you have one more equation, half QV. When to use this, the first one, the second one, or the third equation, it depends. When you have the value of capacitor and the voltage, then you use half CV square. Here, half QV, okay, you substitute C with C equal to Q over V, then you get half QV. So you can use either this, which equation depends on the parameter or the physical quantity, the value that you have. That's it for subtopic 2.1. We have two more subtopics to go. Okay, the second subtopic is 2.2, charging and discharging of capacitor. Here we have three objectives. First one is state physical meaning of time constant and use tau equal to R times C. And then the second objective is sketch and explain the characteristic of QT and IT graph for charging and discharging of a capacitor. And then equation for discharging and for charging. First equation Q equal to Q naught exponent negative T over RC is for discharging process. For charging process, okay, you use this equation Q equal to Q naught 1 minus exponent negative T over RC. Okay, the first objective is now state physical meaning of time constant. Circuit here refer to capacitor is charging. Okay, you connected the capacitor to the battery here. Then capacitor is charging. The charge accumulate on plate of capacitor. So the time constant. Okay. Physical meaning of time constant. This mathematical equation is, we use equation time constant. The symbol used is tau equal to R times C. R is the value of resistance for your resistor here. C is of course the capacitance of the capacitor. Tau equal to time constant. Okay. During charging process, the meaning of time constant, it is the amount of time. And tau is time, so it is the amount of time, and RC circuit takes to charge the capacitor to about 63% of its final or its maximum value. Okay, from the equation time constant equal to R times C, The greater the value of time constant, the more slowly the charge is stored. Tau refer to time. When you have the higher value of tau, it means that the more slowly the charge is stored. The charge accumulated on plate of capacitor is 60% of its final or maximum value. Okay, definition of time constant when the circuit or the capacitor is discharging. How you know that the capacitor is discharging? Here there is no battery in the circuit here. You just have the capacitor and the resistor. So capacitor, it is the ability to store the energy. So when the energy is needed, it will deliver the energy to the resistor here. Any device that need the energy, here the capacitor is discharging. So the time constant for discharging process of the capacitor is the circuit takes to discharge the capacitor by about 60% of its initial charge, meaning that the 60% is already goes to the resistor. So in terms of amount of charge left on the capacitor is 0.37% of its initial value. Okay, after this we refer to the graph of charging and discharging of capacitor. Okay, what happens during a charging of capacitor? Okay, here switch is not closed, so there is a gap here. Capacitor is not charged. So in order to charge the capacitor, we need to apply a voltage and current to flow. So this switch, to close the switch here in order to charge the capacitor connected with the resistor here. This is the parallel plate of the two capacitors not charged yet. So what happens when the switch is on? So the capacitor start charging. Current start flowing from the battery. Capacitor start accumulate the charge on each plate. Okay. Instantaneous charge. Okay, the equation for charging of the capacitor, instantaneous charge Q. Okay, Q equal to Q naught 1 minus exponent negative T over RC. Q is the instantaneous charge, meaning that the charge on the plate of the capacitor at given time. When you have the time, you can substitute in this equation, then we know what is the instantaneous charge on a charging capacitor at that moment. So Q naught 1 minus exponent negative over RC. Charge will rise from 0 to its maximum value when the potential across the capacitor equal to potential provided by the battery. Okay, the graph that you have is exponent graph from 0 to its maximum value. Charge accumulate on the plate of capacitor. The charge, the current will stop flowing when the charge achieve its maximum value, and the potential difference across the capacitor equal to the potential difference across the battery, or the potential provided by the battery. Okay, voltage across capacitor. As the charge accumulate increase, same goes for the voltage across capacitor. It increase as more charges are accumulated on the plate up to the maximum value equal to V maximum V across the battery. Okay, here you have the capacitor charging when the voltage across the capacitor equal to voltage across the battery is stop charging. Current through resistor is maximum initially and decrease as charge on the plate increase and become zero when capacitor is fully charged. So this is the equation for instantaneous voltage across the capacitor. We here refer to the instantaneous voltage across the across the capacitor. And V0 is value from the battery, 1 minus exponent negative tau over RC. So current through resistor is maximum initially and decrease as charges on the plate increase and become 0 when capacitor is fully charged. Okay, in terms of current, here this is the equation for current. I equal to I naught exponent negative tau over RC. Voltage across capacitor increase, but then for the current decrease. So that's why the equation for current is I naught exponent negative tau over RC. But for V and Q, okay, similar equation, you just substitute parameter of Q equal to CV. So C constant and Q increase, V also increase. Okay, this is the second objective. Sketch and explain the characteristic of QT and IT graph for charging and discharging of a capacitor. Let's say you need to sketch a graph of Q against T for charging and discharging. Here refer to charging process. Charging, how do you know it is charging process? Because the charge here increase up to its maximum value during charging process. Time constant just now is 0.63 of its maximum value Q naught here. So you get the tau here equal to R times C, the resistance that you use in the circuit times the capacitance. Okay, for the current when Q is maximum, okay, this is okay when the, during this charging process, okay, the current initially is maximum value. After it pass the charge to the capacitor, the current will decrease exponentially. So tau is the time for the current decrease to 37% of its maximum value. This is the first graph is Q against T, and then the second graph is I against T. You need to know how to sketch these two graphs during charging process. And taking the tau, let's say you have the graph, taking the tau or determine time constant from the given graph. Just now is charging process. What happened during discharging a capacitor? How you know it is discharged? So you remove the battery from the circuit, and then capacitor will act like as a battery. So it will deliver the energy needed by the resistor here. So positive charge from plate A begins to flow through the resistor R and neutralize negative charge at plate B. But the current will flow from the capacitor to the resistor. Just now the current start flow during charging, the current start flow from the battery. Initially, the potential difference or the voltage across the capacitor is maximum. When the charge is maximum, Q equal to CV, C is constant, so V also maximum. V naught equal is as V naught and maximum current I naught refer to the V naught, I naught and Q naught refer to maximum value flows through the resistor R. When part of the negative charges on plate B is neutralized by the positive charges, the voltage across the capacitor is reduced. So voltage depend on the total charges on the plate. So the process continue until the current through the resistor is 0. At this moment, you can say that all the charges at plate A is fully neutralized and the voltage across the capacitor becomes 0. When there is no charge across the capacitor, it voltage also becomes 0. Potential difference between the plate of capacitor is 0. Okay, this is the graph of Q against T and I against T during this charging process. During this charging, Charge start from its maximum value and decrease. Current delivered from the capacitor to the resistor or any device that need energy. So initially the current, okay, maximum after the charge has been used to deliver the energy, then the current goes to zero. Direction of current is in opposite direction to the charging process. That's why we plot like this. Current through the resistor decrease exponentially with time. So both graph are exponent. Exponent graph. Okay, in terms of the equation, okay, charge on this charging process. When the statement refer to charging process, then you use equation to you use this equation to determine the instantaneous or the charge on plate of capacitor Q. Q here refer to the valence charge on the plate of capacitor during this charging process. The charge still less on the plate of capacitor. Q naught is the maximum value. Okay, next we come to the subtopic 2.3. Capacitors with dielectric. For this subtopic, okay, define dielectric constant. Okay, you have the term dielectric here. I will explain later. Describe the effect of dielectric on a parallel plate capacitor. Calculate capacitance of a filled parallel plate. C naught epsilon naught A over D. And then use dielectric constant epsilon R equal to epsilon over epsilon naught. And then use capacitance with dielectric. So I will explain how to use this equation. First, I go through parallel plate capacitor in vacuum and filled parallel plate capacitor. Okay, parallel plate, the simplest form, as I said, it consists of two parallel plates here. The plate should be a conductor. Capacitor of equal area A and separated by a distance D, and the space between the plate is vacuum. Okay, you connect this to capacitor to the battery, and then you have the charge accumulate on each plate of capacitor. Depends on its terminal. Terminal positive require positive charge. Negative terminal will have negative charge on top of it. Okay, so we have one capacitor here. The charge capacitor. Plate have charge of equal magnitude but opposite in sign. Don't talk about the zero charge. And the potential difference will be across the plate is produced. When we have positive and negative charge, there will be a potential difference between the plate of capacitor. Calculating capacitance. Just now I said capacitance does not depend on Q and V. So the capacitance depends on the geometrical factor when you design the capacitor. It is proportional to the area. A plate area, and then inversely proportional to the separation D, distance between the two plates, and then between the two plates there is a gap, whether it is vacuum or you fill it with the dielectric. So for capacitance of air filled or vacuum, how to calculate its capacitance is C equal to epsilon naught A over D, geometrical factor of it, and then plus what you fill up inside the gap. Okay, when you have dielectric material in between the two plates is now, so your capacitance is C equal to epsilon A over D. The term C naught will refer to when you fill it with vacuum. The gap is filled up with air or vacuum. Okay, epsilon naught refer to permittivity of free space, vacuum, and D distance between the two plates A area of each plate, and epsilon is permittivity of dielectric material. Here is what is meant by dielectric. So dielectric is an insulator or non-conducting material such as rubber, glass, paper, and so on. Why we need to use dielectric between the gap of the plate? What is the purpose of dielectric? When a dielectric is inserted between the plate of a capacitor, the capacitance increase. So the main purpose to have dielectric between the two plate capacitor is to increase the capacitance. When you increase the capacitance, that means you can store more charges per fixed voltage applied. If the dielectric completely fill the space between the plate, the capacitance increased by a constant factor, dimensionless constant factor, epsilon r, which is called as the dielectric constant. So each dielectric has its constant value. That is the property of a material and varies from one material to another. Property of the material depends on the material that you use as dielectric. Okay, this is the value of dielectric for certain material. You don't need to memorize all this. Definition of dielectric constant. Define dielectric constant is a ratio between the permittivity of dielectric material between plate and the permittivity of the air, which is epsilon r equal to epsilon here is in with the dielectric, epsilon naught is vacuum. So capacitance of capacitor with dielectric, we substitute epsilon with epsilon r times epsilon naught. Same is permittivity, and then time geometrical factor, the area and the distance between the two plates. And then you get epsilon r times C naught. C naught is epsilon naught A over D just now. So simplify the equation, is become epsilon r times C naught. C naught is capacitor in vacuum. The gap is filled up and just had air fill or vacuum. Describe the effect of dielectric on a parallel plate capacitor. Okay, dielectric effect on parallel plate capacitor. Let's say here you have a parallel plate. When the charge accumulates on each plate, okay, you have a electric field. Electric field from positive terminal to negative terminal, as you have learned in subtopic in topic 1, uniform electric field. Initially, the plates are separated by a vacuum and connected to a battery, and so the charge will accumulate on the plate of capacitor. Then you remove the battery. When you remove the battery, the charge is constant. Okay, the battery is now removed and the charge on the plate remain constant. Okay, you charge the capacitor, positive plate and negative plate. You have the electric field from positive plate to negative plate. Then you insert the dielectric material. When the electric is placed in the electric field between the plate, what happens is that the molecule of the dielectric tend to become oriented. Okay, look at this diagram or this figure. It is on the molecule of the dielectric. So the positive end pointing toward the negatively charged plate, and negative end pointing toward the positively charged plate. The result is built up of positive charge on one surface of the dielectric and negative charge on the other. So what happened to the electric field line? Electric field line here from positive to negative terminal of your capacitor. Number of field line reason the dielectric is reduced. Conceptual question. When you insert the dielectric, electric field will reduce. Your electric field, when you have the dielectric, E less than E naught, E in vacuum. So recall the equation V equal to E times D, parallel plate, uniform electric field in parallel plate. You use equation V equal to ED. So V decrease, since E increase, D constant, so V also decrease. So from Q equal to CV, is constant. Q cannot go anywhere. There is no decay. We talk about the ideal capacitor here. Q is constant, V decrease from Q equal to CV, C constant, V decrease. So, no, C is not constant, sorry for that. Okay, when you have the dielectric inserted between the two plates of the capacitor, okay, your Q constant, V decrease, so C increase. And when you have the dielectric. So this can be proved by this experiment or by this figure. You can see that when you have the capacitor, here is this vacuum between the two plates of capacitor. Okay, this is the value of its voltage. And then when you insert the dielectric, you can see the voltage increase. To prove that the voltage in vacuum when you have the dielectric compared to the voltage in vacuum. Dielectric is added between the plate of charged capacitor. Q remain as I said just now, as I explained just now. Voltage decrease to balance the increase in capacitor where the charge is constant. Okay, this slide we refer when you don't have the battery connected to the capacitor. If the dielectric is introduced while the potential difference is being maintained constant, still connected to the battery. Just now you remove the battery and insert the dielectric. Here, battery is still connected to the capacitor. Then what happened? Okay, the charge increased to value Q equal to epsilon R Q naught. Okay, when you connect to the battery, you have higher storage, your capacitance increase, then the battery can pump more charges to the capacitor. That's why the value of Q increase. Q equal to epsilon R times Q naught. Epsilon R more than 1. So Q, when you have the when you insert the electric, is more than Q in vacuum because the capacitance increase. So charge also more charges can be placed. V here is equal to V of your battery. Then you can store the maximum value of charge. Already explained this just now, previous slide. Okay, I already covered all the three for subtopic 2.3. Use dielectric constant, use capacitance, use dielectric. That's all for today's lecture. And then next topic, you will learn about electric current and direct current circuit. Okay, for the attendant purpose, please scan this QR code. Time given is just 1 week to submit the form. So that means that you attend or you view this lecture. Okay, thank you again. Assalamualaikum warahmatullahi wabarakatuh.
Kalau nak cakap apa
Tapi dah ni lah.
Kalau okay.